Welcome back. With this video, we begin our discussion of transport layer protocols. Recall that transport layer is the fourth layer in our network architecture, and transport layer protocols use the services that are provided by the network layer. And applications use the services of transport layer to send and receive messages. The contents of this video are end-to-end protocols. We are going to discuss what are the desired functionalities of transport layer protocols and what are the challenges in designing such protocols. UDP and TCP are the two most commonly used transport layer protocols. By the way, UDP stands for User Datagram Protocol and TCP stands for Transmission Control Protocol. So by the end of this video, you would know how do these two protocols, UDP and TCP, turn host-to-host packet delivery service that is provided by the network into a process-to-process communication channel, which is used by applications. And you will know how does TCP establish and tear down its connections. Because the transport layer protocols support communication between applications running at end hosts, these protocols are also called end-to-end protocols. The messages that are exchanged at the transport layer, between two parties are not supposed to be intercepted by intermediate nodes, which could be routers and switches. Here is a list of functionalities that an application might want from a transport layer protocol. Might be expected that the protocol guarantees message delivery from one end to the other. Might be expected that it delivers messages in the same order that they were sent. Might be expected that it delivers messages at most once. Might be expected that it supports arbitrarily large messages, and there should not be any upper limit. It's expected that the protocol supports synchronization between the sender and receiver. It's expected that the protocol allows the receiver to apply flow control to the sender so that the sender does not overwhelm the receiver. And it's also expected to support multiple application processes on each host, and we'll see that UDP and TCP both do this. And note that this is really not an exhaustive list. There are many other requirements that may be put here. For example, we have not included security, right? There may be timeliness requirements in the case of real-time applications. Now let's look at some of the challenges that transport layer protocols face. The transport layer protocols use the services of network layer, and we know that IP only provides best effort service. The underlying network might drop messages, it might reorder messages, it might deliver duplicate copies of a given message. Although there is no upper limit to the size of a message, but packets invariably have an upper limit on their size. So the network would limit messages to some finite size. And we know that IP datagrams are limited to 64 kilobytes. And lastly, the network may deliver messages after arbitrarily long delay. The challenge for transport protocols is to develop algorithms that turn these best effort services provided by the underlying network into the high level of service required by application programs. Transport layer protocols use different algorithms to give different set of services to application programs. As we will see, UDP gives a certain kind of service and TCP gives certain different kind of service, and the functionalities that TCP provides depends on the algorithms that is used in the protocol. The first transport protocol that we are going to look at is User Datagram Protocol, or UDP. UDP extends host-to-host delivery service provided by the network layer into a process-to-process communication service that is used by applications. Note that many processes typically run on a given host. UDP adds a level of demultiplexing, which allows these multiple application processes to share the network. Other than this, UDP does not add much to the datagram service. And therefore, it's basically a simple demultiplexer. Applications attached to the network using sockets. And here is an illustration. So we have these applications. They are attached to the network using sockets. And for identifier, UDP uses what is called port number. And UDP uses these port numbers both for the source as well as the destination to identify the sending and receiving processes. This is UDP header format. It has 16-bit source port and another 16-bit destination port ID. And it has 16-bit length field and another 16-bit checksum. We'll come back to these a little bit later. You might be wondering, how does the sender know which source port and destination port to use? The commonly used approach is to have servers accept messages on what is called well-known ports. These are ports that range from 0 to 1023. And the list of these ports is maintained by IANA. And for example, SSH server listens on port 22, HTTP on port 80, and HTTPS on port 443. So if a process is trying to send message to, let's say, an HTTP server, then in the destination port, it's going to use number 80. And selecting source port is easy because this port number is only used to receive messages. And therefore, clients are assigned what is called ephemeral ports. It's any port that is not currently in use that's assigned by operating system. The concept of port mapper service generalizes this idea of well-known port. It's possible to have just one well-known port on which an end host can run a port mapper service. And depending on the service that the sender wants to connect to, the port mapper can inform the sender of an appropriate destination port to use. Other than these two source and destination port fields, the header has 16-bit length and another 16-bit checksum fields. The length field indicates the size of the header, which is 4 and 8 bytes, plus the size of the payload, and this is indicated in the units of bytes. And lastly, this 16-bit checksum field is computed using this UDP header, this payload, and pseudoheader. Whether pseudoheader contains 4 items. Contains the source IP address, the destination IP address, and the protocol number, plus this length field that is already present in the UDP header. So this length field is used twice in computing this checksum. The ports are implemented as message queue. When a message arrives, UDP puts this message at the end of the queue, and when there is no space in the queue, UDP simply drops this message, right? So there is no flow control. However, the queue size is usually a configurable parameter. When an application wants to receive a message, it basically pulls a message from the front of the queue, and when the queue is empty, it just blocks until it gets a message. Because UDP does not provide any reliability service, it is used by applications that can tolerate packet losses. They are typically used in multimedia applications like voice over IP or video streaming. They are also used by certain helper applications like DHCP. In the case of applications where we require integrity of the sent messages, we use Transmission Control Protocol or TCP. In contrast to UDP, TCP offers reliability. It is connection oriented. That means before starting data transfer, connection has to be established. And once the data transfer is completed, that connection has to be turned down. TCP also provides guaranteed in-order delivery of a stream of bytes, usually referred to as byte stream service. TCP provides flow control where it protects the receivers from being overrun by senders. TCP also provides congestion control where it controls the amount of data that a sender is injecting into the network. Note that these seem kind of similar, but actually these two are quite different. Flow control is concerned with controlling the sender from overrunning the receiver. On the other hand, congestion control is concerned with controlling the amount of data that sender sends into the network. And of course, like UDP, TCP also provides demultiplexing, right? So this is also there. The sliding window algorithm is at the center of TCP design. However, when we studied the sliding window algorithm, we considered two endpoints that were connected directly by a point-to-point link. However, as TCP runs over the internet, the connection between A and B might involve several links going through several routers. And so when A and B are connected by point-to-point link, there is no need to establish connection. However, in the case of TCP, the endpoints could be separated by several hops, and therefore TCP uses an explicit connection establishment phase followed by transmission of data, and at the end there is also a connection teardown phase. The second issue is that of round trip time variations. So when we talk about two endpoints that are connected by a point-to-point link, the round trip time on this link is almost a constant. So for all different transmissions, A can set its timeout according to this one round trip time that it can measure between A and B. However, in the case of TCP, this sender might be sending to different hosts at different times, and depending on the distance of the receiver or the destination from A, the round trip time is going to vary. And since we are talking about in the internet, these variations in round trip times could be very significant. It could be from just a fraction of milliseconds, could be hundreds of milliseconds. And not only that, it may be that just within one connection, the round trip time might vary a lot, because different packets might take different paths through the network, and therefore just setting a timeout based on one round trip time is not sufficient. And therefore, in the case of TCP, the timeouts are adaptive. Another issue is that, which was not present in the case of single point to point link, which happens in the case of TCP, is that packets may get reordered in the internet and they may arrive out of order at the destination. In the case of endpoints that are connected by single point to point link, the end systems are designed to support the link at its full capacity, and therefore one can set the sending and receiving window sizes as delay bandwidth product. However, in the case of TCP, the destination is not directly connected to the sender, and furthermore the destination might be supporting several other TCP connections, and therefore TCP has a mechanism using which it learns the available resources on the other side. And lastly, and by the way, this refers to the flow control mechanism that we talked about. And the last one is the congestion control mechanism. And so TCP also needs a mechanism which allows the sending side to learn the capacity of the network. And again, in the case of TCP, the packets traverse several hops, and some of the links may have, they could have either a small capacity, or maybe they are carrying a lot of traffic from other sources to other destinations. And therefore, if the senders send more data, then, for example, this router can send over this link, then the queue on this router is going to fill up, and that's going to result in congestion. And therefore TCP has a mechanism to deal with congestion explicitly. Recall that at transport layer, the unit of messages are called TPD, or Transport Protocol Data Unit. In the case of UDP and TCP, we also call them segments, or we call them generically as packets. As I mentioned earlier, TCP is a byte-oriented protocol, and that means that sender writes bytes into a TCP connection and the receiver reads bytes out of the TCP connection. And this fact is a service, right, that TCP offers to an application. However, TCP itself would not transmit individual bytes over the internet. When an application process writes bytes into a TCP connection on the at the source side, then this data is stored in buffer until a reasonable amount of data has been collected, and then TCP puts this data in a segment and then sends to the destination. The TCP connection on the receiver side then collects the data that arrived in a segment in a receive buffer, and then the application process reads the data from this receive buffer whenever it wishes to. And one thing that I want to note is that the TCP connections are duplex, although in this case we have shown that this is the sender and this is the receiver, but on a single TCP connection, this side can also transmit data that would be received by this side. Now we are going to look at TCP header. So the first 2 bytes contain the source port, and the next 2 bytes contain the destination port identifier, just as in UDP. And combined with IP addresses, so a source port and source IP and destination port and destination IP, all these 4 fields uniquely identify a TCP connection. Then these 3 fields, 4 bytes of sequence number and 4 bytes of acknowledgement number plus 2 bytes of advertised window, they are used by TCP's sliding window algorithm. TCP is byte oriented. In TCP, each byte has a sequence number. This sequence number field contains the sequence number for the first byte of data that is carried in that segment. Then these 2 fields, acknowledgement and advertised window, they are used to send information to the other party. Acknowledgement carries the acknowledgement of the received data, and advertised window is used for flow control, as we will see in the next video. These 6 bits labeled here as flags are used to relay control information. And the flags, for example, are syn, fin, ack, urg, push, and reset. We will see what they mean in the next slides. The syn flag is used to establish connection, and the fin flag is used to terminate a connection. The ack flag is set when this packet contains acknowledgement field. Right, so when there is an acknowledgement here that's valid, then this ack flag is going to be set. The urg flag indicates whether a segment contains urgent data. So when this flag is set, this urg pointer field becomes valid, and this indicates the portion of the data where non-urgent data begins. So in the payload, the first bytes would contain urgent data, and the data after this urg pointer would contain non-urgent data. When the sender wishes to push some data to the receiver, it will set this push flag. The effect of setting this flag is that the receiving side of the TCP connection will then notify the receiving process that it has received some data. And lastly, this reset flag signifies that the receiver has become confused because it expected some segment that it was not expecting to receive. And the setting this flag indicates that it wants to abort the connection. Because of these options, the TCP header has a variable size, and therefore there is this header length field, and the unit of the number that is indicated in this field is 32 bits. Lastly, there is 16-bit checksum field, which is used pretty much the same way as UDP. It is computed over the TCP header, the TCP data, and the pseudo header, which as we saw is made up of source address, destination address, protocol field, and length fields from the IP header. Algorithm that is used by TCP to establish connection is called three-way handshake because it involves exchange of 3 messages. Here is a timing diagram of three-way handshake. So assuming that the server is ready to accept connections, so it has called socket bind, listen, accept, and now it's ready to accept incoming connections. And then on the client side, you do socket and connect. So the first message that the TCP connection on the client side is going to send is a SYN segment, and in this segment the SYN flag is set, and the sequence number field is populated with a random sequence number. When the server receives this, it's going to respond with another segment that's called SYN-ACK segment. In this segment, these SYN and ACK flags both are set, and the sequence number is populated with another random number that is chosen by the server client, the server TCP connection. And in the acknowledgement field, the number that the client TCP connection said, it's incremented by 1 and it's put there. And in TCP acknowledgements, the number that is sent is always the byte number that the other side expects to hear. And so since the server already got this byte number X, I mean this in packet counts as 1 byte, then it's going to ask for byte number X plus 1. It's important to note that the starting sequence numbers are chosen randomly and they're chosen independently by the two parties. It is possible that two endpoints A and B establish TCP connections using same ports again and again. And so when it happens, these connections are called different incarnations, because the source IP and source port across the different incarnations remains the same, and same for the other side. And when this happens, then it's possible that a segment that was transmitted earlier may show up later on and confuse the connection on one of these two sides. So suppose while this connection is being established, some previous SYN segment shows up on the server, and as a result the server is going to send this SYN-ACK segment. However, in this SYN-ACK segment, it's going to be sending U plus 1 in the acknowledgement field. And so if the client uses different sequence number when it's trying to establish different connections, then the client would be able to detect and reject this SYN-ACK segment. Similarly, if an ACK shows up later on, then the server can detect that it's a delayed ACK, because currently it's using a different sequence number for its transmission. So it's using Y, so it expects an acknowledgement with sequence number, or rather acknowledgement number as Y plus 1. However, in this delayed ACK segment, the acknowledgement number is going to be something different, and therefore the server would be able to detect that it's a delayed acknowledgement message, and it's able to reject this. This is a TCP state transition diagram. These diagrams are very useful when designing protocols. And this state transition diagram shows only part of the TCP state transition diagram. It only shows connection establishment phase. These boxes indicate the states in which a TCP connection can be in at any given time. And the connection moves from a state to a state based on events, and it also generates actions when it makes these transitions. And so those events and actions are written in this format. So event slash action. So here what it means is that the connection would move from listen state to SYN received state when it receives a SYN segment, and as a result it's also going to send a SYN-ACK segment. So let's try to understand the connection establishment using this transition diagram. So all TCP connections start in this closed state. So in the case of server, So it does this passive open and it goes to the listen state. And when it receives a SYN segment, right, we have seen before, it sends a SYN AG segment and it transitions to this state SYN received. And when the other side receives this SYN AG segment, remember that that side is going to send an AG segment, right? And so from this state, this server is going to transition to established state once it receives this AG segment. And in this case, it does not generate any message, so there is no, the action part is empty, right? It's only event. On the client side, again, the connection begins, close the state. Once the client performs an active open, right, sends a SYN segment and it transitions to SYN sent state. In this state, it's going to wait for a SYN AG segment, as we just saw before. And once it receives this SYN AG segment, right, it's going to send an AG message to the server, and then this connection also transitions to established state. And as I said before, this is only a part of TCP state transition diagram. So for example, for all of these messages, there is timeout, right? That's not shown here. What happens when the server, for example, receives a SYN, sends a SYN ACK message, but never receives an ACK, right? So eventually it's going to time out. And same for, the client side. What happens if it sends a SYN but never receives a response? So those transitions are not shown here. So just to make you realize that this is only part of the picture. As for connection teardown, both sides close the connections independently, and this is also called symmetric close. So let's say we have this client that wants to close the connection. It's server, and in any case, as I said, this, so the closing of the connections is done independently, and so it could be that the other side wants to close the connection first. So whichever side wants to close the connection first is called an active side, and the other side is called a passive side. And so just to maintain our previous example, suppose the client starts the connection release process. So it's going to send a FIN segment, and this segment would have a sequence number, right, which is not going to be something arbitrary, but it's going to be in line with the connection. So whatever sequence number and the amount of data it had sent, it's going to be according to that. But just for example, let's say that this sequence number is equal to X. And so as a result, the other side is going to send an ACK, and here the acknowledgement number is going to be X plus 1. And then this side is going to send its own pin segment. It will have a sequence number, again compatible with the sequence number that this connection is using. Let's call it Y. And then client is going to send an ACK, and the ACK number is going to be Y plus 1. And so here we need to realize that when this ACK is received at the client, the connection from the client side is closed, but the client should still be available to receive data from the server because the server has not closed the connection from its side. And lastly, like SYN-ACK, these two segments can be combined into one FIN-ACK segment. To summarize, transport layer protocols turn host-to-host delivery service that the network provides into a process-to-process communication service that applications use. Also saw that while UDP provides simple datagram service where packet losses can happen, TCP provides reliable message delivery service. Both of these protocols, UDP and TCP, allow multiple connections to share the network. TCP uses a three-way handshake algorithm to establish connection. In this establishment process, three messages are exchanged, namely SYN, SYN-ACK, and ACK. And lastly, TCP acknowledgements indicate the next expected byte number. The material that we covered in this lecture is discussed in detail in Peterson and Devi, chapter 5, sections 1 and sections 2.1 through 2.3. And in Tenenbaum and Weatherall's book, chapter 6, section 1 and sections 2.1 through 2.3. Here is a short quiz for you. You might want to pause this video and find out which of the following statements are correct. The correct options are A, B, and D. A says transport layer uses services of network layer, and that's correct. Network layer is above transport layer. B says UDP uses port number for demultiplexing, and that we saw is how UDP demultiplexes the incoming segments. Then C says UDP is used for file transfer application. That is not correct because in the case of file transfer application, we require reliability. The file that is sent should be the same that the file is received. And therefore, UDP alone is not sufficient for file transfer applications. The fourth option says TCP segments may arrive out of order, and that is correct because if we have two endpoints that are connected by a single point-to-point link, this will not happen. But in the case of TCP, the endpoints may be far apart. There may be several hops in between, so different segments may take different paths, and at the end arrive out of order at the destination. So this is correct. And the last one says TCP connection establishment involves exchange of two messages. That is not correct because the algorithm is three-way handshake and the number of messages that are exchanged is not two but three, and they are SYN, SYN-ACK, and ACK messages. So this is wrong. That's all in this video. See you next time.